Yeah, that's I'm talking about the title there, and AMPERE stands for Active Magnetosphere and Polar Electrodynamics Response Experiment. When it changed from a NASA Explorer proposal to something to NSF, I was actually flipping through the E's in the dictionary, looking for another E because Explorer had to be replaced by some other E word, and so that tells you how long ago that was when I was actually looking at a dictionary, paper dictionary, to do that. Yeah, that was interesting. So let me put this in a little bit of context because I know that there's a varying degrees of familiarity with different aspects of the space environment, the solar environment, and the magnetosphere. So we'll start at the sun because we all know everything starts at the sun. And even though the sun is not the center of the universe, it's the center of our universe. All of the energy on the Earth eventually comes from that thing. And so I see some resident experts in the room who are very, very familiar with the sun's dynamics and flares and coronal mass ejections, and that is a sequence of a coronal mass ejection. And that sequence is something I showed when I would be teaching a course on space physics and introducing people all at once to what I call electric space, which is a term that Tim Eastman. I think Tim Eastman introduced that term when he was starting off the GEM program. Was electric space. So I'd introduced that. I would use that. So I use this to sort of show these things because people who have never looked at these kind of images of the sun are astonished. Now, what's interesting for the Earth space environment is if the Earth were not looking at the sun like this, but over here, and then that mass ejection of magnetized plasma then encounters the Earth's magnetosphere, and then a geomagnetic storm is driven, or maybe not driven, depending on what the magnetic field in the flux ropes is. That's when things get very interesting from a magnetosphere, ionosphere, thermosphere standpoint from high-latitude electrodynamics. Here are some of, let's think back now to almost prehistory, certainly the previous millennium, because that's where the germ of these ideas came from to do this. And think back to what we knew back in the we'll call it the 1900s, about the storm time system. And so this is a sequence of images here from the Dynamics Explorer satellite, and some of us remember what that was. Some of us even remember Bob Hoffman giving talks on Dynamics Explorer. But I remember what an absolute revelation it was to see the entire auroral oval all at once, and then see during the course of a storm, and I think these are like 10 minutes apart, snapshots of the evolution of the oval during active times and seeing how much it expanded. And I'll try it again. And then that's one effect of these coronal mass ejections when they reach the Earth. Another effect is when the solar energetic particles, which takes about 8 minutes or a little bit longer because they're speed of light type particles, when they reach the Earth, and this is what happens to imagers that are trying to image things. And we often ran into this, for instance, on the messenger program, as there'd be a storm, and then the image people would say, we're getting all these artifacts in our images, and we're wondering what they are. And I says, oh, those are charged particles. What's that? So that's another thing that happens with these things. And then this is what we're most familiar with, and we still use these venerable indices, the SIMH or DST index, where it initially goes positive. That's associated with the compression effects of the leading edge of the sheath, or maybe of the actual storm itself, usually the sheath. And then a negative going in the DST is the buildup of the ring current. It's still kind of negative going here, and then it begins to recover. So these initial phases, main phase and recovery phase, are defined in terms of those indices. And as you can see, there's in the auroral electrojet indices, which is high latitudes, there's an awful lot of dynamics within all of these sort of gross sort of main phases. And so that there's been a lot of work done in statistical analyses, organizing by DST and storm phase and so forth, and cutting it finer. But as you can see, there's a lot of dynamics in there. But as of the 1900s, this was kind of the state of the art in terms of what we knew about what storms did. And we were just learning that coronal mass ejections were one of the primary drivers of geomagnetic storms. So that's the era, if you will, of the germination of the ideas that eventually turned into AMPERE. So here's now it's Bill's fault. Is a cartoon of the magnetosphere. So the Earth is in there. This is the magnetopause, a cartoon of that, the magnetosheath. This is where the plasmasphere is here. The radiation belts, which are very dynamic, are here. And this is a static cartoon view of that system. The challenge is, how do you monitor the dynamics of this system, which can reconfigure in 10 to 20 minutes? When even in low Earth orbit around the Earth, it takes a satellite 100 minutes to get around. That's 10 or so reconfiguration times of the system. How on earth do you try to get a global view of that? That's why imaging the aurora was so important. The hard lesson from polar is that you can't really get the electrodynamics from that. But the basic paradigm when a southward IMF encounters the Earth is that magnetic reconnection occurs here. Magnetic field is pulled across over the northern and southern polar caps, reconnects back here, and those flows come back in here. And as I was saying earlier to I think it was Art, we were having this conversation, that for all of the other fascinating phenomena in the magnetosphere, its only real job is to get the flux from here to there. Everything else is just ancillary in terms of the magnetosphere. It has to satisfy that boundary condition. And so this magnetic convection, which has been around, we're heading up on 60 years since that was first published. That concept has been around for a long time. And that's a very fast-moving system. Let's look at that in the plane, looking at it from the sun, just to give you a feel for what we're seeing. So we're looking at it from the sun. These are some of those field lines that are reconnected, that are going into the screen away from you. That's establishing a potential then that maps down to lower altitudes. Plasma within the magnetosphere is connected along magnetic field lines like that. And then at Earth, we have an ionosphere. So that potential sets up electric currents that flow down in the evening side and then up in the morning side. And they actually connect to currents that are linked to the plasma within the magnetosphere, the so-called region 2 currents, region 1 and region 2, because you could use polarward or equatorward, but 1 and 2 are much shorter. And so that's all they mean. But most of the current actually flows that way. So you can see that these currents that are flowing along these magnetic lines of force down to about 120 kilometers altitude or so actually reflect that total magnetospheric circulation, that magnetic circulation of the system. So knowing that, here's a cartoon looking at it from the top. You look at the sun is up here. These are the upward currents in the evening, downward currents in the morning. This is the electric field or the closure currents. If all you had were those poleward currents, which are the ones directly driven by that imposed potential, if that's all you had, that's kind of what the electric field and the closure currents would look like. It turns out if you work out the energetics of this is an energetically very expensive way to do that interaction. And if the system can reduce the energy that is exchanged in that, it will. That's what the magnetic perturbations would look like if you had that. But what the system really does is set up so-called shielding currents, the region 2 currents, which are the opposite polarity of the region 1 currents. They actually serve to shield the electric field out here and shunt much of the current. And they actually allow more current to flow than if you didn't have the region 2 currents in the total system. So that's kind of what the system looks like from the Earth. That's what the magnetic perturbations would look like if you were coming across from dusk over to dawn. You'd see anti-sunward perturbations, sunward, and then anti-sunward in the magnetic field is what it would look like. Here is a view, a very famous view, but this is sort of a three-dimensional rendering of that. These are the sun is now, I think, here. Anti-sunward flows over the polar cap, dawn to dusk currents over the polar cap, region 1 currents coming down, closing to region 2, and then the same thing over in the afternoon. And so that's the relationship of these field line currents to the whole convection system that I'll be talking about for the rest of the talk. And so now what I'm going to talk about is these field line currents and their relationship to that and how we diagnose them. So this is the best that we could do in the 1900s, up to about the 1900s, in terms of diagnosing what that field line current system looked like. And one of the revelations of the 1900s was when we finally launched satellites that could be in the IMF permanently, so we could actually see what was coming. And then you could statistically map things, and if you organize them by southward BZ, you get this kind of a pattern. Dusk is over here, and you have downward current, upward, downward, and upward current shown there. And then for southward IMF and for northward IMF, you can see the currents are weaker, and they tend to be a little bit higher latitudes. But you notice there's an awful lot of commonality in these patterns. And because you're dealing with single satellite statistics, you're having to use all of the data and bin it together, even though the system is changing faster than it takes a low-altitude satellite to get across the polar cap. So there's an awful lot of smearing between states that goes on in these kind of analysis, but that was the best that could be done back in the, as I say, the 1900s. So the problem is that the system is not the average. If you want to understand what the system really does, your statistics can only get you so far. They can only get you to a crude sort of static cartoon like that. Dynamic events have convection in different latitudes, different local times. The gradients are much sharper than those smeared patterns that you saw. There are structured flows, structured precipitation, and currents that necessarily imply dynamics and mass transfer that you cannot estimate based on those smeared patterns. In addition to that, during storms, the system is very different scales. It goes to different latitudes. The potentials that are involved are very different. The total currents are much larger, and there's about 100 times more energy involved in the dissipation of the system. And so that you're trying to do, if you want to understand storms and you want to do it statistically, that's a really hard thing to do. And so as I was gradually beginning to appreciate the field back in 1995 or so, I realized if we're going to make any real progress on this, we need a quantum advance in the kind of observations that we have. And that was not a new idea. A lot of people were doing that. Radars were going up. The people were motivating, putting in lots of ground magnetometers. The whole concept of the DAISY concept was driven by that. And the approach that I took was a little bit different. I'm going to skip that. And I'm also going to skip that. And I'm going to skip that. So what do we need to do to make real progress? Well, we have to make fundamental measurements of fundamental quantities. But what do I mean by fundamental quantities? Something that's an MHD quantity, like current, electric fields, flows, something like that. Because what we had tried to do was to use the polar satellite using multiple wavelengths of the aurora to try to diagnose the conductivity and try to extract the electrodynamics from that. It turned out that the aurora is too far removed in electrodynamics to allow you to really close that problem. And it wasn't for lack of really smart people trying really hard. It just couldn't be done. So we needed fundamental quantities. They had to be globally distributed at all local times, all latitudes. And they have to be on a cadence that's short relative to the reconfiguration time of the system. And that means you're driven to a constellation. So let's talk about fundamental quantities. This is my box model of the magnetosphere and the ionosphere that helps me organize some of these things. First of all, there's flows, which is related to electric fields in the magnetosphere that way, and it's related to convection in the ionosphere that way. And those two are linked by the field lines, which are nominally equipotentials, unless you're an aurora fan, like Bill Lotko is an aurora fan, and then you object, and you say, wait a minute, that isn't always true. But for the purposes of my box model, it's true. And then the next moment in the Vlasov equations is momentum. And these are the momentum equations which are related to perpendicular currents. And if you integrate those along a field line, you get field-aligned currents. And those are the things that then flow to the ionosphere. And those are related to the perpendicular currents in the ionosphere, which are familiar friends, the Hall and Pedersen conductances. And it's the divergence of those that's related to that. And the nice thing about that is that those currents have to be conserved between low and high altitudes if you're below the time regimes where you care about that. And these currents are conveying the stresses. So these are conveying potential and flows. This is conveying stresses, which is related to momentum. And if you want to talk about energy, the magnetosphere at high altitudes is the dynamo for the system. Let's set neutral winds aside for the moment. And primarily the ionosphere and thermosphere is the drag on that. And the dominant energy flow is electromagnetic energy flow, which you can measure with the Poynting flux. So now let's look at some of the quantities we have here and see which ones are the fundamental ones that we would have access to measure. And the electric fields are one of them. And that's why people were going after chains of radars and the super darn high latitude radars, because if you get the electric field, you can begin to diagnose some things about that. You can begin to get pieces of the momentum, and you get part of the dissipation part of the system and the energetics of the system. So if you get the electric fields, you're making a lot of progress there. If you can measure magnetic fields and derive field line currents, you notice that you get this part, and you can actually diagnose what's happening at the high altitudes and relate that to the distributions of plasma, at least through these uncertainties, and you can close on the energetics of that. So those are two of the key parameters that you want to try to measure to try to close that system. So formally, this helps set the stage in that sense. So this is the idea. If you have a satellite at low altitude flying through this kind of a system, it will see the magnetic perturbations created by these currents. And it will see primarily between these two sets of currents right in there. That's where the biggest perturbations will be. So if you have low Earth orbiting satellites passing through the currents, they will detect them. You can use those currents, and then ionospheric currents actually shield that so that you cannot diagnose these field line currents from the ground. What you see from the ground are the perturbations related to the Hall currents. And that's removed from the field line currents that I showed in the previous slide by two different layers of the conductivities. And so it's a little bit harder to do that. That's how people were first, as in people, as in that people, Art and Kamide and others, first used ground magnetic perturbations through the conductivities to try to derive some of these things, which is where the AMI procedure derives from. And you can see this is all converging on that bill.
Yeah, don't you still have a problem? So you observe a magnetic perturbation, and it has sources associated with field line currents, and depending on the altitude of the satellite, also with Pedersen currents.
No, the Pedersen currents. There's a very simple thought experiment you can do, is that the Pedersen currents actually accomplish the if you have a filament current, okay, and it goes into a uniformly conducting plane. Anywhere you measure things on the upward side of the filament current, it looks like a line current, infinite line current. And so what the Pedersen currents actually do is they make these look like infinite current sheets that are going down below you. And so you don't have to treat what the Pedersen currents are really doing. The competing perturbation is really from the Hall currents, and if you get up above about 500 kilometers, they're less than a 10% effect. So it's the fact that the ionosphere is there and the Pedersen currents are flowing actually allows you to ignore that.
So I'll just rephrase: ionospheric, perpendicular.
The Hall currents are the issue. The Hall currents are the issue. Yeah. Now, what that means, the converse of that, is that above about 500 kilometers, you can't use those measurements to tell you anything about the distribution of the Hall currents, which give you a signal that's in the parallel to the magnetic field direction, whereas the field line currents are giving you signals primarily in the perpendicular to the magnetic field direction. Whereas if you get to lower altitudes, you can begin to diagnose some things about the Hall currents, and that's what Larry Zanetti did with MagSat back in 1983 or whatever it was. Yes?
So what's the relative position of the gap between the region 1 and region 2 and the aurora?
The primary discrete precipitation, which is the downgoing electrons, which create the brightest aurora, are co-located with upward currents. So they will be located in the upward region 2 currents in the morning and the downward region 1 currents in the evening. So the oval is actually shifted a little bit towards the morning relative to the field line current and the convection distribution. So that's, and there are a lot of people here who can correct me if I'm saying anything that's incorrect, and they're welcome to do so. So good, excellent. Okay, so where the germ of this started was in a conversation I had with Dave Klumpar in May in Baltimore on the veranda of the Baltimore Convention Center, where he was at Lockheed at the time and was working with people on building the first generation of Iridium satellites. And he knew something about what the Iridium satellites were going to do, and then he put me in touch with some of the engineers because they were just going to be launching in 1996 and 1997. And that's what the Iridium constellation looks like, of 66 operational satellites, 70 satellites, 72 with spares on orbit. There are 66 satellites. That is the Iridium Operations Center in Leesburg, Virginia. There's a magnetometer on every satellite as part of the attitude control system, the avionics of the satellite. It had a resolution which we regard as good scientists, we turn up our nose at that and say, well, that's a terrible magnetometer. You can't do anything with that. Except that the relevant metric is the signal to noise relative to the Birkeland currents, and the Birkeland current perturbations are about 300 or larger for moderate activity. So your signal to noise is about 10 to 1. Okay, if that's really the noise signal to digitization resolution is about 10 to 1. Okay, so in principle it could work. The fact is, it takes about 10 minutes for this satellite to get where that one is, because there's 11 in each orbit plane, 100 minutes, so it's about 9 minutes between satellites. So you resample all along the orbit tracks every 9 minutes with that. So that's what we realized in the mid-90s, that if you could make this work, if you could get that data, if you could look at the data and see that it worked, you could do something with that. How many of us were out of school in 1996? Yeah. Okay. Yeah. No, you can keep your hands down. It's okay. You know, some of us have to be. You know, we have to be proud of what we can be proud of, right? So it's a great idea. Okay. So it should be an easy thing to do. Yeah. Nope. So I first proposed this, and I kept the first proposal to NSF about this, and I was really brave, because I wrote the proposal for what I wanted to do with the Iridium data, and I didn't have any yet. I actually wrote this proposal for data that I had never seen. And amazingly, the NSF was very visionary, and I asked for 80K per year over 3 years, and they actually gave me 40K for each of 2 years to sort of see if this thing could actually, is there a there? Let's put a low investment, potentially high return. Well, it was actually critical, because in my conversations with Iridium, it really mattered that I actually had funding to do this from the National Science Foundation. That was enough cachet to get them to listen and realize that I wasn't some flake. Well, maybe that's not true, but I at least I was a relatively serious scientist, and so that opened the door. If I didn't have that funding, it would have been very difficult to get that door open. So I'm so glad I wrote the proposal without having any data, because I couldn't have got the data if I hadn't have written the proposal. And if I couldn't have written the proposal without having the data, you can see kind of the catch-22 you're in on this sort of thing. So it was interesting. So anyway, that was the first thing. So I remember when I was talking with them, I fell off my chair when they actually called, because I'd been trying, and finally they called me back. And we got to talking about it, and I described what I wanted, some test data, and afterwards they said, well, if we have to go to the bother to pull this stuff out of the database, what if we just send it to you all the time? Would that be a problem? No, that'd be great. So anyway, we began receiving data for free. They sent it to me for free, because I had to tell them I could pay for my time, but I can't pay you for this stuff. So the first file that I got, it was an enormous file. But it was ASCII, and it was Julian date that went on for like 30 characters, and then there was the satellite identification, and then there was the measurand, which was like another 30 characters, and then finally there was the magnetic field in Teslas to 6 decimal places. The signal I'm looking for is in the 8th decimal place. And so I looked at that, and I thought, oh my God, I hope that isn't how they sent it down to the ground. And it turned out it was a formatting thing in how they were querying their database, and they did have all the actual raw bits. So anyway, I did get that, but it was a very slow cadence, 200 seconds between samples. That entire current system I was describing is about 5 degrees wide. In that amount of time, the satellite moves about 16 degrees. So it's not fast enough. Okay, that's the fundamental problem we ran into. So we began talking with Motorola to upgrade to a higher cadence, and we were actually working on a mission of opportunity through a NASA Explorer AO to do this. And I was working with Motorola at the time. They were one of the prime investors with the Iridium system. And then we got to actually working on the mechanics of how the proposal would go. It's going to NASA. We would need a subcontract. And they said, wait a minute. This is a NASA. This is going to be a government subcontract. We can't even send money from our commercial side to our government side. Because if you're doing a government subcontract, you in effect have to follow what's called the Federal Acquisition Regulations. I think that's what it's called, the FAR, anyway. And it means that the government has access to your books. And there was no way that the commercial division of Motorola was going to do that. They couldn't even open their books to their government side. And so that killed the proposal right there. They said, we're not doing this. We can't do it. Absolutely not. Never mind that they were going bankrupt. So then the Iridium bankruptcy hit, and it was reconstituted at the behest of the U.S. government after they shed their debt, because they couldn't. What happened, of course, is they were building this as a mobile phone network. Right. They weren't counting on all those towers going up. And they were betting on getting lots of people in cities to get Iridium phones. But the cell phone market took off at exactly the same time they were launching their satellites, so their market disappeared out from under them. And so they had invested all of this money and their business case went south. So they had these enormous loans, $5 billion it took to launch those satellites commercially, and they didn't have any revenue. Essentially, they had almost no revenue. But the system was up there, it was working, the phones were kind of clunky and awkward, they worked anywhere, which was great. And then the US government discovered that, but if we blew up all the cell phone towers in Kosovo to deny communications to our adversary, we couldn't talk to our people either. And that's when the US government realized we need that system. And so that's when the US government stepped in and said, yes, you're going under, but you're not going under. Dear investors, yes, you're losing your shirts. You go ahead and sue. Good luck with that. We're taking the system over. Is basically what it is. So a new company was reconstituted at the behest of the US government. That's kind of how it went. I actually had one colleague came up to me at a meeting while it was very uncertain whether Iridium would survive or not, and was saying, this is going to be so great, we're going to do spectroscopic observations as the Iridium satellites re-enter. Don't you think that's great? I had to admit that I wasn't too enthusiastic about that. Anyway, but this is the data that we get from the old Iridium system in 20 minutes. That's it. That's all of it, polar to 40 degrees in 20 minutes. That's how long it takes the magnetosphere to reconfigure, and that's it. The average spacing, I mean, it's 10 degrees, 20 degrees in some places between points, and you don't know when in that 20 minutes it was taken. So that's the problem of data sparsity that I was talking about. What I did is I did some work where I put together a bunch of satellites in one orbit plane from the old data back in 1999, and then time shifted it so it was all at the same latitude. So they're all time shifted to that satellite so that they're all sampling the same latitude at the same time. And then you can see that the measurements that are coming out of the system are lining up. And this is when I was writing an abstract, and I sent it to the Iridium engineers, and I said that we're getting signals here on the order of about, maybe 50 nanoteslas or so noise, 70 nanoteslas noise. And they said, no, the noise is several hundred nanoteslas. And I said, no, that's my signal. Because they did not know that this was real signal. So the classic example of somebody's noise is somebody else's signal. Is exactly what that was. But that's what I had to do to prove to myself that this was actually going to work. If we increase the cadence, it would actually work. Here's an example. If I take this is original DMSP F13 magnetometer data. If I decimate that to 30 nanotesla resolution and one sample every 200 seconds, that's what you get. You can see you completely missed this. And you also completely missed that at that time resolution. That's the problem with that sparse pattern that I showed before. It's just not often enough. If you do a 20-second sampling, this is what you get. It actually captures the large-scale currents reasonably well. And then if you decimate that to 30 nanotesla resolution, you can see that if you were going to design a system that could just barely do it, that would be it. And that's what they have on the satellites. So that's what we did. The problem, though, is a telemetry problem, because that magnetometer data was coming down in a spacecraft health and telemetry packet, heuristically that big. The magnetometer data was that much of it, tiny fraction of it, okay? And what they're selling, of course, on the satellites is bandwidth. They're not going to burn their precious commodity that they sell sending more of this data down so I can have more of that. That's not an option for them. So what they came up with was a very clever solution, which is to take a telemetry protocol which is on the satellites to send a message which basically says, help, something is going on, that the satellite sends, a separate telemetry packet. What they did is they configured something to put the magnetometer data in those event messages, which are generated by the satellites and then pushed. And they set the software up to generate those automatically and push those over containing just magnetometer data. So they took advantage of like an emergency communication system to shoehorn in what we needed for the AMPERE data, and that's what they set up. It was I'll have to say, my respect and admiration for the people in the commercial satellite business has evolved dramatically. They're fantastic at what they do. They're very good at what they do. Okay, well, that wasn't the end of the story. Okay, so we'd figured all that out. Technically, it was fine. We were gearing up for another mission of opportunity to NASA. Now we were working with Boeing because they had gone bankrupt. We weren't working with Motorola anymore. We were working with Boeing. Interestingly enough, it was the same people. Exactly the same people. They just were getting paid from somebody else. That's all it was. It was the new company, and we actually had to work to change the AO language for missions of opportunity because the AO language said flight, flight equipment, and we had to change it to flight experiment to allow modification of stuff that was already on orbit. Okay, so we did that, and then King George III was elected, and he canceled the Explorer AO in the middle. He canceled it to do the Exploration Initiative, which was the Lunar Reconnaissance Orbiter. And that MIDEX canceled that opportunity. So I remember getting a phone call from somebody saying, hey, did you see that? Is that a problem? And I said, is that a problem? You bet it is. So that was canceled. Okay, so the next opportunity was the RBSP AO. And we were proposing to that. And I included the HF radars, and that was when Superdawn was expanding to mid-latitudes. And I included that as a funded part of what we were doing because the electric fields are very important for the radiation belts and understanding convection and all that sort of thing. Right, okay, so the major weakness we got was HF radars don't work. And the proposal was declined for that reason. Okay, yeah, that was interesting. And somebody actually told me, you wouldn't believe who was on the committee who said that. But anyway, that was interesting. So finally, I got smart. It's only taken me 10 years to this point, right? So
why does that refer to HF radars? Sorry, I'm not in this community. So.
Well, it's specious. It means that what HF radars do is they try to detect echoes of plasma irregularities,
Yes.
and then get Doppler shifts to look at velocity flows. And we couldn't figure out what the reviewer was saying either. And interestingly, neither could the NASA officials. But it had come out of the panel as a major weakness. That was then something that the NASA official could not get around. They could not fund the proposal. They had to decline it, even though it was specious.
Isn't it true that they don't really know how that diagnostic works in detail?
They don't know in detail. They don't know in general terms how that diagnostic actually works. It does, though.
With uncertain errors.
There are uncertain errors. Yes, yes, yes. So it does and it doesn't. So I think we now know who was on the panel. So anyway, so I got smart, and it was interesting because an NASA official said if you hadn't had the radars, we could have funded it. Right. Okay. So finally, I proposed it to NSF as a facility. I briefed NSF. I finally got tired of being nice, and I finally started to just go down to NSF and say, you guys should do this, period. End of discussion. We know how to do it. This is what has to be done. Fund it, damn it. Sort of thing. I know we're being recorded. So anyway, it was then selected for funding, and we had a Boeing subaward on there. It was a subcontract because half the money was going to Boeing to do it. Okay, so I was, as was alluded to, I was a magnetometer scientist for the Messenger magnetometer on the same day that the Messenger spacecraft did its first flyby of Mercury. So that's the first time a spacecraft had been to Mercury in 30 years. And we were seeing the magnetic field from that for the first time and getting images of part of the planet that had never been seen before. Okay, so this is like the defining rush of a scientific career, right? So on the same day that that happens, I get a call from NSF saying, we need to see the details of the subaward because we don't pay fee on engineering services. And I knew what that meant for the AMPERE proposal. It was basically torpedoing the whole AMPERE proposal because if they were not going to pay fee on a subcontract, then we couldn't do it through NSF. And it was a legal contractual problem. We actually got to a point months later, so that's why I say it was the best of times, it was the worst of times. It was on the same day. Months later, we had a make-or-break telecon with the APL director of contracts with the #2 person at NSF in charge of contracts. And we actually got to the point where NSF said, that director said, oh, well, looks like we won't be able to do this because they could not give us the money for the subcontract to Boeing to implement this. Great idea, right? And so actually the engineer and I, who had been first working for Motorola and then Boeing and now works for Iridium, same guy, he and I worked out what if we just bought the data? Data buy, period. There's a price. This is how much per bit. We just buy the data. So that's what I said. Well, what if we just bought the data? And then NSF, well, that would be okay if you can demonstrate that it's a fair and reasonable price. Well, we had already figured out how to do that. So there was 2 seconds where it couldn't happen, and then we just slivered this under the door, and then NSF said that might work. That's how we did it. And literally what I did was I took the statement of work, subcontract, statement of work, and I went in there and did it, product description. That's what I literally did. I just changed the title to a product description and then changed a little language, and that's how we did it. So we did it. Summer of 2008, Iridium data in 2009, and then we got full coverage since then. There's 8 months that we've skipped, and then Block 1 continues to live beyond its lifetime, and Iridium Next is going up, and the first satellites have already gone up, and they have magnetometers on them, and we can do AMPERE on that. Where's my time? What's my time? I feel like I'm about 40 minutes in.
Yeah, you are.
Okay.
Same degree of sensitivity, resolution.
It's the same resolution. The limiting factor on Block 1 is the attitude system, because the attitude system uses a combination of gyroscopes, magnetometer, horizon sensors, and sun sensors. And they do a Kalman filter on board to try to get the attitude. And they get it to like 1/10 of a degree, which if you work out how much of a magnetic field perturbation that is in a background field of 50,000 nanoteslas, it's huge. The new satellites are using star cameras. It's just much more cost effective. And that's an order of magnitude, 2 order of magnitude improvement in the attitude knowledge. So the limiting factor in the 70 to 100 nanotesla noise in Block 1 is because of the attitude solution. In Block 2, it's going to be vehicle magnetic contamination noise. I already know that. But it's going to be smaller. It'll be better by about a factor of 2, maybe 3 in terms of noise. The baselines will be quite a bit better than that. So Boeing had to do a software upgrade and installation. This is on an operating commercial system where all the satellites are actually part of something that's providing customer service, and they are changing the flight software on the satellites. Turns out they do that all the time. And this was just part of a build. They keep doing updates to their satellites all the time. And it was just part of their build and was in their regular build process. The data comes down to the Science Data Center at APL, and then we generate products. One thing that we did in Block 1 was we could do promotions to higher rates of sampling. We did that for getting a lot of data on geomagnetic storms. This is a block diagram of what it looks like. This is the satellites. There's a real-time telemetry stream. There was a delayed telemetry stream. That all gets ingested at that Leesburg facility that I was describing on a couple of leftover servers that they had. And then they ship it to us by secure FTP, and then we do the science processing on it from there. So that's how that works, and it's working. It's happening right now. So this is a side-by-side example of what was originally coming down from the Iridium satellites what we've been getting 24/7 basically since January 2010, and then what we get in the density of sampling when we're at enhanced rates, doing high rate. That's deceptive because it looks like it's all filled in because I'm showing 10 minutes of data. Actually, there's 33 points on there that are moving. That's what it really is. It's only 33 points is that they're moving in those planes. And if you look over 10 minutes, it looks like you're filling it in. How we do analysis for the field line currents is we take these perturbations, we do a spherical harmonic fit to that, and we have to be very careful how we do those functions so that we can use recursion relations to get the curl out of that. And this is where, if there are contributions from the currents underneath us that were not related to the currents that we're flying through, those will disappear here because they will not show up in the curl formally. And then we can derive products, which is when I was first working with Jesper Gerloff on this, and we were looking at something, and he said we were looking at something in the northern hemisphere, and he says, "Gosh, I wonder if we only had stuff in the southern hemisphere." I said, "Yeah, well, let's pull that up. That's not a problem." And he sort of said, "Right, you've got both hemispheres," and so that you can do conjugacy things. So we can calculate the total current. And we can calculate it on the day side and the night side, northern hemisphere, southern hemisphere, and calculate ratios and all that sort of thing, and see some of the dynamics. And you can see that we're resolving dynamics on the 10-minute, 20-minute time scale of these things that are happening. This is kind of fun. This is the St. Patrick's Day storm 2013. And if I can find my cursor, this is the entire day. And we have these summary movies on there for every day that we have data. Oh, now it has to find the cursor again. But let me start that. So what you're seeing here is you're seeing satellites go across. So we do every 2 minutes a frame. So you see the satellites going across. It's really cool to visualize how this pattern gets made because you can see the satellites actually filling in. And then you see the spherical harmonic fit and the field line currents. The storm started there, and along about 10 o'clock it gets more intense. And I'll just let that play, and maybe we'll play it again. And then you can just figure out what's your favorite part to look at it. So you're actually able to diagnose something about the evolution of the electrodynamics through a geomagnetic storm. And when I've been looking at a number of these, the challenge, then you'd say, well, then understanding geomagnetic storms should be duck soup, right? Because you've got this data, you got this phenomenal resource. The problem is figuring out what's in common between the different storms because they're so dynamic and so different. There are things that are in common. Do you want to see that again or not? Nope. Okay. I didn't have any. Got to see it again. So here's an example for what we're learning relative to what we knew before. If you take pure states of the system, that is when the interplanetary magnetic field is very stable. So I can trust my advection time to Earth, and I know the system didn't change, and I select only those intervals. If I put those together for northward IMF conditions, that's what you actually get. That was the statistical result previously. Similarly, for southward IMF, this is what you get, whereas that what we had previously. Now you can really see that these are both mixtures of different states and smearing things. So that this is never what the system looked like. Yeah?
So the left columns are the old data, which is much lower.
Single satellite Ørsted statistical analyses.
But
Yep.
it seems like the magnitudes of the two are
The magnitudes aren't that bad.
So
Yeah. Well, this is actually 0.18, 0.3. This is getting up to 1, 0.5, something like that, or larger. Especially this is much larger. Yeah.
the southward cases like
There's a southward case, it's really not that bad because they tend to stay that way for a while. And it's basically how large is the delta B. And you can resolve that reasonably well. Yeah. Now, this is much lower than what we get individually because this is still, in a sense, a statistical average. We collected a bunch of events, so there is some smearing, and that smearing is happening in both. Yeah. But it's the separation of states that's interesting. And the real reason why this works is that we can afford to take only 1% of the data and still get a really robust pattern because we have so much data. Oh, people have been doing a lot of work with this. A lot of people in this room have been doing a lot of work with this. This is one of the neat things about this is you get the data out there and then you begin to see all the creative ideas that people are doing things that I, A, never would have thought of and B, never would have had the expertise to do. And it's really, there's almost nothing more gratifying than to see a whole bunch of people that I didn't even know did this stuff beginning to do this and send me papers to look at and so forth. It's really been amazing. So let me talk about a couple of these, just to show how much of a difference it makes. And this is why using it in things like AMI is so important. This is Rick Wilder did some stuff where he was taking AMI and doing a derivation of electrodynamics. He was working with Jeff Crowley on this. This is without AMPERE, and that's including AMPERE. Same interval. And then here's another interval where not using AMPERE and then using AMPERE. Again, exactly the same interval, and which basically is proving the point that lack of observations is lack of observations. You just don't know. If you don't have the observations, you don't know. There are things you can do to try to help yourself regularize your solutions and so forth, but there really is no substitute for observations. This is some work that Gang Lu did, where she was taking the AMPERE data and then assimilating it into AMI for this geomagnetic storm, which is April 4-5, 2010, I believe, or 5-6, 2010. The really cool thing about this, and sorry I'm skipping over this, is that she actually ran the thermosphere models for this and compared the densities actually observed on the Gochi and the CHAMP satellites with the simulations using the AMI inversions that included AMPERE. And because the satellites are slightly eccentric, the densities look a lot higher in the northern hemisphere than they do in the southern hemisphere. And if you look at a constant altitude surface, you can actually see these traveling thermospheric waves in the density profiles. And the agreements here, what's nice about this is that the agreements, and these are the same color bars, the agreements that are showing up there are actually showing that if you're getting the electrodynamics that way, you're getting end-to-end actually evaluations, and is a kind of a really powerful proof that if you can get the electrodynamics right, we really have a handle on determining how the thermosphere and ionosphere are behaving. I'm going to skip some of this stuff because I want to get to some other cool stuff. These are good movies. So one of the questions that arises is, how does the system go from nothing to something? For instance, how do you go from quiescent to that? Does it happen where first you drive the region 1 currents and then the region 2 currents form? Is it really kind of like that evolution right there? Is that how it happens, or is it some other way? So that's one of the things that I looked at. I looked for cases where I was looking for onsets of activity, and this was almost one of the first things that I saw in the data as I was looking at it, is I would see a little bit of activity here, and then all of a sudden there'd be something that started on the night side, and it was after things started on the night side that the whole pattern filled in. And it was only after it started on the night side that the whole pattern filled in. So I did some work with a summer student looking at onsets, and that was how we found things. We looked for onsets in the total current. We did a fit to identify onset times, and then put together a bunch of cases. And this is the magnetic perturbations, and this is the field line currents, and it's going to pause at the onset. You notice there's both region 1 and region 2, and then the real full-fledged system forms afterwards. So you get a little region 1, region 2 on the day side, and then afterwards it fills in on the night side after you have the night side onset, i.e. substorm onset. And so the region 1, region 2 currents are intimately linked, both on the day side when you're starting the convection, and then after the night side when you start the return convection on the night side. The other thing that we did then is we compared that with the ground magnetometers, putting the ground magnetometers and binning them together to see how these onsets are affected there. Same pattern that you see here in the field line currents, but the black arrows are the ground magnetometers. What you'll notice is that nothing really starts until after substorm onset, and then the ground magnetic signals start. Notice the huge asymmetry here in the ground magnetometers. There's almost no asymmetry in the field line currents. That's got to be a conductivity difference between the pre-midnight and post-midnight sectors. So this is how it looks like it maybe really works, is if you go from quiescent to activity, you start field line currents here, the polar cap is expanding. when you finally start the reconnection process on the night side and the return flows, that's when you develop the whole system. And it's not until you have that full convection and the convection cycle is closing that you get that. So you do not start with the region 1 currents and then add the region 2 currents. They come together. So that was something we were able to figure out. Let's see, I think I'm going to fly through all of this stuff. It's kind of neat, but we're going to skip it. Ooh, models don't do very well. Okay, we'll just say that. Okay, this is storm time. This is storm time model of Weimer and the space weather modeling framework. Snapshots of the field line currents. That's a time profile of the total current. And then this is a regression coefficient of actually field line current distributions. The correlation coefficients are generally above 0.25. They're positive mostly. That's nice. Okay, you know, I got that. This is called job security, right? So the modelers have some work to do. These are low resolution models. They can do a lot better if they increase the resolution. There are all kinds of things. But now we have a global metric we can use to really tell how well are they doing. It's not just model versus model, model versus observations. And so that's really handy. This is just so cool. I wanted to confirm whether, you know, we're actually seeing the same thing. Let's take two totally different independent data sets, the ground magnetometers and the AMPERE field line currents, put a movie together. Oh, you see this is going off scale, so I have to decrease by an order of magnitude to show how that's working. So let's look at this movie. This is the 5th of August 2011 storm. Where's my cursor? There we are. This is just fun to see. So the green dots are ground magnetometers from SuperMag, and the red stuff is the field line currents from AMPERE. And just watch it. There's all sorts of fascinating questions that come to mind, and you do come away convinced of that they're looking at the same system. They really are looking at the same system, and sometimes the ground magnetometers aren't in the right place, but you know, we know that, right? So there has to be a way to stitch these together, and Amy is one of, you know, this kind of assimilation scheme, but this basically convinces you that there's a way to get there from that, because they are seeing the same system. And so surely there's fruitful work to be done there. I'm just going to let this play out because I'm almost done. And there's some more cool dynamics, I think, that shows up later in the day. Nope. Okay, so this is, they've been launching the next satellites because the Block 1 Iridium satellites are on their way out. They launched the first 10 back in January. I don't know when the next launch is planned. This was a real nail-biter of a launch because this was the first attempt of the Falcon 9 after the failure that they had, the spectacular failure they had in the launch pad where it blew up on the launch pad. And you've all watched that video of the thing blowing up on the launch pad where it's looking like, and then all of a sudden there's this bam that goes off on the top, and then the whole thing collapses. And it was pretty spectacular. Well, this was the first Falcon 9 launch after that. And so Iridium, SpaceX, everybody is crossing everything they have 3 times, actually double checking everything, but it worked. So that worked. You know, the first version is good. Next is going to be better. Next is on Block 2. It's supported. The satellite constellation is the identical configuration, so it's the same spacing between satellites, the same orbits, all of that. So all the positions of the satellites are the same. The attitude determination now is about 1/10 of a nanotesla, so that corresponds to about a 16 nanotesla error in your magnetic perturbations. This is how good it's going to be. So that's below the noise level. It's below the digitizational level. So the attitude solution is now, that's not a contributing factor. That's not a limiting factor anymore. Before it was. The magnetometers are basically the same. The only problem is that there's more spacecraft noise in the magnetometers, so that there's on the order of something like, and I don't really know the number for sure, it's tens of nanotesla. So it's on the order of the digitization size. It's enough so we can see it. How much I'm going to be able to beat that down, we don't know. But the other thing that's really exciting about it is that they have changed. They're not using this little message thing that I described, where the satellite collects data for like 30 minutes and then sends you a packet, because that limits your real-time response to like 30 minutes or something like that, which is, when it only takes you 10 minutes to resample it, that's kind of hurts to realize that I've got this system resampling every 10 minutes, but I can't get real time that good. On the new system, they implemented AMPERE in a different way. They actually wrote it into the software from the beginning. Now what the system does is it downlinks every magnetometer sample as it's taken, so that every 3 minutes they send us a file which is, here's the data we just got. So that our latency is like 3 minutes from on-orbit acquisition. And then we know that it only takes us about 5 minutes to produce products from that. So we're really, really close to having something that's in true real time. Now, paying for it and actually supporting personnel to keep something working in true real time, that's a different story. But technically, it's feasible to do that. This is what our 24/7 AMPERE data looks like now. This is what it will look like under next. We actually ran some intervals like that. And in fact, that's how it's being sampled right now. They're doing a promotion to that rate from now through September to support the MMS tail campaign. And so because the MMS tail campaign is all about substorms, we can see substorms. So that's really important for that. And that's the latency issue. That's all I had. I'm happy to take any questions. If people want to stay after and talk, I'm happy to entertain any discussions you might have. Thank you so much for the invitation to come.